In late 2024, an otherwise unremarkable backyard observation begins to draw attention, not because of what it claims, but because of what it shows, and just as importantly, what it does not resolve. Astrophotographer Ray, working from his own backyard, documents a familiar object, a comet, cataloged as 3I Atlas. At first glance, this appears routine. Comets pass through the inner solar system regularly. Their tails flare, fade, and disperse. Most are cataloged, measured, and quickly forgotten. But as Ray continues observing, a pattern emerges that is at least worth slowing down for, not because it defies physics, but because it sits uncomfortably at the edge of expectation. This is not a story about conclusions. It is an examination of observations, assumptions, and unanswered questions anchored strictly to what is shown, what is measured, and what remains uncertain. Ray captures this when he begins imaging Comet 3I Atlas from his backyard telescope, focusing not on the coma or nucleus, but on the ion tail, the plasma stream shaped by solar wind and electromagnetic forces rather than dust.
So these are the latest pictures of Comet 3A Atlas that I took from my backyard. And I was looking at the ion tail. Let me run the time lapse for you.
What Ray is showing here is not an interpretation. It is raw observation. Sequential images taken over time processed into a time-lapse to highlight motion and structure within the ion tail. Ion tails are not unusual. They can stretch tens, sometimes hundreds of millions of kilometers under the right conditions. They are shaped by the solar wind, often pointing directly away from the sun, sometimes displaying kinks, rays, or disruptions as solar activity fluctuates. Ray explains his processing here by running time-lapse imagery and zooming through orbital simulations. He overlays trajectories, compares distances, and cross-references publicly available ephemeris data. None of this is proprietary. These are standard tools available to amateur and professional astronomers alike. What matters is not that Ray is doing something novel, but that he is persistent across multiple dates. According to Ray's observations, Comet 3I Atlas passed Mars, past Earth, and is now on a trajectory toward Jupiter. He marks December 19 as the date of closest approach to Earth. He notes January 11 as the present reference date for his later measurements. At this point, the comet is approximately 2.8 astronomical units from the Sun. On December 19, it was closer, roughly 1.8 AU. These are standard heliocentric distances, and they matter because they typically correlate with activity levels and brightness. Ray notes that over roughly 23 days, the comet's visual magnitude remains near 11. This is not visible to the naked eye, but it is accessible to modest telescopes. What catches Ray's attention is not the brightness itself, but its apparent persistence. Under many circumstances, comets dim measurably as they move away from the sun. Volatile outgassing decreases, ionization rates change, activity can drop rapidly. That is the expectation. Ray is careful to show the numbers rather than assert the cause. He then shifts focus from brightness to motion.
And December 19th, Comet 3 Atlas was here. And now Comet 3 Atlas is now slowly moving from this lane all the way and going towards Jupiter. So with the time when it reaches Jupiter is like somewhere between March 15th through March 19th. It's quite far where 3 Atlas is from Jupiter right now, and it is flying at the incredible speed to reach there.
Ray states the comet's velocity at approximately 46.9 kilometers per second, or about 105,000 miles per hour. This is fast but not unprecedented. Some long-period and hyperbolic comets achieve comparable velocities, particularly near perihelion. Ray further notes that Comet 3I Atlas is projected to approach Jupiter between March 15 and March 19 at a distance of roughly 0.35 astronomical units. That is not a close flyby by gravitational standards, but it is close enough to be dynamically relevant. At this stage, Ray begins to layer interpretation on top of observation. He remarks on what he sees as an efficient trajectory, one that passes Mars, Earth, and now aligns toward Jupiter. He suggests the path appears optimized in a way that resembles gravity assist planning. This is where separation becomes critical. The path itself is observable. The efficiency is a judgment. Orbital mechanics routinely produce trajectories that pass near multiple planets without any guiding intelligence. Low-probability events occur constantly in large datasets. The solar system has had billions of years to generate rare alignments. Ray's assumption here is not evidence of intent, but an expression of how visually striking the geometry appears. The analysis remains grounded as Ray shifts to a different question: proximity. Specifically, proximity between Comet 3I Atlas and a spacecraft already en route through the outer solar system. Ray overlays the trajectory of the Europa Clipper spacecraft, a NASA mission launched to study Jupiter's moon Europa. He highlights dates in late October and early November, particularly October 29 and November 6.
October 29 is when I was noticing this. On October 29, or something like this. You see that? The tail of 3 Atlas is completely showering the Europa Clipper, and they took a picture from there. So I wanted to do one more thing. I wanted to compare 3 Atlas to, not compare, measure the distance between these two. They are 150 million kilometers apart.
Ray shows that during this window, Europa Clipper and Comet 3I Atlas were separated by approximately 150 million kilometers. He emphasizes that the ion tail, as modeled and visualized, appears to extend across that distance. Ray references publicly available statements from NASA and astrobiology sources suggesting that Europa Clipper could potentially be immersed within the ion tail of Comet 3I Atlas. This is not Ray's claim, it is a cited prediction from mission-relevant discussions. Ion tail immersion is not unprecedented either. Spacecraft have encountered cometary environments before, sometimes intentionally, sometimes incidentally. What remains unclear is what, if anything, Europa Clipper detected. Ray does not present in situ plasma data. He does not show instrument readouts. He does not claim anomalous spacecraft behavior. Instead, he stops at geometry and scale. This is an important boundary. The mainstream explanation accepts that ion tails can extend vast distances, especially under favorable solar wind conditions. Projection effects can exaggerate perceived overlap when viewing from a specific angle. Brightness can persist longer than expected depending on composition and outgassing behavior. Accepting all of that still leaves several points unresolved. First, the apparent scale consistency between the modeled tail length and the spacecraft separation remains visually striking. While projection can account for some overlap, confirming the three-dimensional structure requires data not currently presented. Second, the brightness stability remains notable. Ray expects the comet's magnitude to drop towards 16. Instead, it remains near 11 across multiple weeks and increasing heliocentric distance. This does not violate physics, but it does invite further scrutiny. Third, the timing coincides with active spacecraft instrumentation. Europa Clipper carries ultraviolet and plasma-sensitive instruments capable of detecting ionized environments. Whether those instruments recorded anything unusual has not yet been publicly disclosed. Ray acknowledges this gap. He repeatedly states that more data is needed. At this point, plausible natural working theories remain sufficient. Enhanced solar-wind interaction could sustain an extended plasma tail longer than average. A temporary compositional anomaly could increase ionization efficiency. Viewing geometry could amplify perceived tail length without requiring extreme physical dimensions. None of these explanations are mutually exclusive. What is missing are direct measurements: plasma density, ion composition, field interactions. Without them, interpretation remains provisional. As Ray concludes his video, he does not present a conclusion. He presents a collection of aligned observations and stops. That restraint matters. In space science, most mysteries do not resolve with revelation. They resolve with datasets, cross-comparison, and often disappointment. Many intriguing patterns dissolve under closer measurement. Comet 3I Atlas may prove to be entirely ordinary. Its tail may behave exactly as physics predicts once full solar wind data is applied. Europa Clipper may have passed through nothing of consequence, or it may contribute a small incremental data point to our understanding of comet spacecraft interactions. At present, the observation window is closing. The comet is moving outward. The geometry is changing. Opportunities for confirmation are diminishing. What remains is not an answer, but a record. Ray's footage documents a moment in time. It provides a basis for questions, not conclusions. Until additional data is released, if it is released, the observations sit where they should, unresolved, provisional, and open. In space science, that is not a failure. It is the starting point. Before we end, I want to take a moment to speak directly to you. If you found this exploration meaningful, if the questions raised in this video made you pause, reflect, or see interstellar space a little differently, then I ask for your support. Creating content like this takes time, careful research, and a genuine effort to present uncertainty honestly rather than sensationally. If you appreciated that approach, please consider subscribing to the channel. Your subscription tells the algorithm that thoughtful, long-form science discussions matter. Liking the video may seem small, but it genuinely helps this content reach others who are curious, skeptical, and interested in understanding the universe beyond headlines. If you have thoughts, questions, or interpretations of your own, I encourage you to leave a comment. Science advances through discussion, and your perspective adds value to this space. And if you know someone who enjoys astronomy, astrophysics, or quiet mysteries like this one, sharing the video helps keep these conversations alive. Your engagement is not just support, it's motivation. It allows me to continue producing careful, grounded content like this, exploring the edges of what we know without rushing to conclusions. Thank you for watching, thank you for thinking critically, and thank you for being part of a community that values curiosity over certainty. Until next time, keep looking up.